There are two ways in order to break a sigma bond. The first method is the heterolytic cleavage, which we went over in most of our reactions in organic one. So let's say, for example, if you had a molecule in here and you want to break its carbon-bromine bond, then the definition of the heterolytic cleavage is that the sigma bond is going to be broken in a way that the two electrons of the sigma bond is going to be transferred to the bromine. So the bromine or the carbon, here I chose the bromine. So the bromine is going to take all the electrons and it's going to leave the carbon electron deficient. So to represent this, you're going to represent it by a positive charge on the carbon, indicating that the carbon lost electrons, and a negative charge on the bromine, indicating that the bromine gained electrons. The bromine already has three lone pairs, and you added two more electrons from the sigma bond. So you would need to show that the bromine here is fully charged and it has two electrons in there. So what you're getting over here is plus charges and negative charges. Here the plus charge is our carbocation. And we said that carbocations, these are very stable intermediate. For these reactions, whenever we want to draw the mechanism for them, you would need to show a full head arrow and the transfer of the two electrons towards whatever electronegative site you have. A carbon is a plus a charge whenever it has three bonds in there. So for carbocations, they do have an empty p orbital, and because they have three bonds, their hybridization is going to be an sp2 hybridization, which is a planar in this case. Because they do have an empty p orbital, that is going to make the intermediate very reactive because they can accept electrons in their p orbital. So always heterolytic cleavage will end up forming cations and anions. And notice that the method that the cations and the anions they are formed from, it's going to be completely different than the other type of the bond cleavage. The second type of cleavage is called the homolytic bond cleavage. And with this type of cleavage, it's going to run by a completely separate rules than the heterolytic bond cleavage, meaning that the intermediate that I'm going to get with these types of bond breaking is different than the carbocation. So let's say if we have something like this, if we have this alkane, and we are doing a homolytic bond cleavage along this carbon single bond carbon, then the way to represent it is simply by a half head arrow. This is going to be the sigma bond. So I'm going to use a half head arrow and I'm going to divide the bond into one electron going to one carbon and another electron going to the other carbon. See the difference in here in the mechanism. Here I'm using a full head arrow and transferring all the electrons to one atom. Here I am breaking the sigma bond in half, and each one of these carbons that are joined by the bond is going to get an electron. So in this case, I will end up getting another intermediate, and that is a radical intermediate. So my point here with the homolytic bond cleavage, you can never get a carbocation. So carbocations here are not going to be our intermediates for the homolytic bond cleavage. Our intermediates are going to be called free radicals. If you look at the geometry of a free radical, so free radicals are sp2 hybridization because they have three groups around them. So the carbon over here is going to be an sp2 hybridization, and the radical itself is going to lie in the p orbital. If I want to compare to the carbocation is still an sp2 hybridization, but the p orbital here is empty. Here, the p orbital has one electron. I know that the capacity of the p orbital is 2 electrons, so this one is still lacking an electron because radicals, they do have 7 electrons, 2 for each bond, and then an electron in here. So the carbon is not octet. This is what makes them very reactive. And they are also considered intermediates. There are several conditions that we're going to use in order to break that sigma bond by a homolytic cleavage. These conditions, they are specifically for a homolytic bond cleavage and not a heterolytic cleavage. So there are 2 reagents that I'm going to use for this type of bond cleavage, or 2 sets of conditions. The first set of condition, I'm going to use light or heat. Whenever you use light, you generate heat in this case. And I don't want you to confuse heat with elimination, because this is not an elimination reaction. Elimination does not happen by just heat. Elimination requires a base. And here I'm not using any base in there. So I'm going to use light, or I'm going to use heat. Or another condition, I can use a peroxide. And a peroxide can either be a hydrogen peroxide, which is H2O2, or it's going to be an alkyl peroxide, which is R2O2 in there. This is the Lewis structure for the peroxide, and the name varies if you vary the groups that are connected to the oxygen. Now, peroxides, they do share a sigma bond between the 2 oxygens. And that sigma bond, because it is between 2 electronegative elements, it is very weak. So that sigma bond can be broken if it is subjected to light. Broken by a homolytic cleavage, and each of the oxygens will pick a radical. So you're going to end up getting free radicals. These are very reactive intermediates, and these are what starts the free radical reaction. There are different types of radicals. So let's say, for example, if we have these radicals over there, and you want to check what's the type of the radical and their stability, the first thing that you need to look for is the carbon that is adjacent to the carbon radical. So this is the carbon radical in here. The carbon that is adjacent to it is just one carbon. So this is called a primary radical or a primary free radical. This one over here has 2 carbons connected to it. Then this is going to be a secondary free radical or a secondary radical. You can represent it by a carbon with a radical. And this one has 3 carbons that are connected to it. So it's going to be a tertiary radical. So tertiary radicals, these are more stable than secondary than primary radicals. And we're going to give the same explanation that we gave for carbocations in organic 1. The reason for the stability of the tertiary radical is due to electron distribution by inductive effect, or the pull of electrons are due to the inductive effect. So if we look at the hybridization of the free radical carbon, this is an sp2. And here I'm considering a tertiary alkyl free radical. So the carbons over here, I do have 3 carbons around the free radical. Each one of them is an sp3 hybridization. I know that the sp3 is less electronegative than the sp2. This means that the sp2 carbon is going to pull electrons away from the sp3 carbons. The more carbons you have, the more distribution of the charge you're going to get throughout the structure. So this radical in here will no longer be electron deficient, or the electron deficient site will not just be focused on this radical. No, it's going to be distributed across the whole structure. And this is the definition for stability. So stability is the electronic distribution throughout the whole molecule in there. You need an even electron distribution throughout the whole molecule. So the more R groups around the radical, the better. This is why tertiary radicals are more stable than secondary and primary radicals. There are the other two types of radicals are allylic and benzylic. Now these are very stable because of resonance. So let's start with the allylic. An allylic group is simply a carbon that is connected. So see this carbon over here. If you have a carbon that is connected to an alkene, then this carbon, I'm going to call it an allylic carbon. So this carbon over here is going to be an allylic carbon. And the hydrogens around it, here I do have 3 hydrogens around it. Those hydrogens, I'm going to call those allylic hydrogens. Normally, an allylic carbon is a carbon that exists on carbon number 3 of the double bond. You always start numbering from the beginning of the double bond. So always the allylic carbon is on carbon number 3 of the double bond. So this one over here, if you look at carbon number 3, there is only one carbon connected to it. So this is called a primary allylic. Now, if you look at the second example over here, this is going to be my allylic carbon. And this carbon is connected to 2 carbons. This is 1 and this is 2. So this is going to be a secondary allylic. And of course, I will end up having my allylic hydrogens in there. So all of these hydrogens, the 2 hydrogens here, I'm going to call them allylic hydrogens. And I'm going to end up having in the third example a tertiary allylic. So again, look at carbon number 3 of the double bond. This is 1, this is 2, this is a 3. And this carbon is connected to 3 groups. It's connected to 1, 2, and 3 groups in there. So that is called a tertiary allylic. And that tertiary allylic will have 1 allylic hydrogen. Okay? Now, when you lose any of these allylic hydrogens, then you're going to end up having a radical. So let's say, for example, I lost one of these hydrogens in there. Then I'm going to end up getting a radical. Then the radical is going to be a primary allylic radical. Same thing, if I lose this hydrogen over here, I'm going to end up having a radical. So it's going to be a secondary allylic radical. If I lose a hydrogen on the tertiary allylic position, then I'm going to end up getting a tertiary allylic radical. All of these radicals that you see, these are more stable than the tertiary radical because of resonance. Benzylic carbon. So the benzylic carbon is the carbon that is connected directly to the benzene. You need to have a benzene, and it's the carbon directly connected to it. So if this carbon over here is directly connected to the benzene, it has only one carbon on this side, then I'm going to call this a primary benzylic. And the hydrogens that are around it, these hydrogens will be called benzylic hydrogens. Okay, so all of those are benzylic hydrogens. So let's say, for example, if I go ahead and I lose one of these hydrogens in there, then I am going to end up getting in a free radical. And that free radical in there, so I'm going to end up getting a free radical here on this carbon. And that free radical is going to be a primary benzylic radical. Same thing on this carbon over here. This carbon is the benzylic carbon. So always locate the carbon that is directly connected to the benzene and see how many carbons it's connected to. So here it's connected to 2 carbons. Then this is going to be called a secondary benzylic. And if I go ahead and I lose just one hydrogen on the secondary benzylic, then I am going to end up getting a radical, in this case on the secondary. So that is going to be a secondary benzylic radical. We're going to do the same thing on the tertiary benzylic. And it's tertiary benzylic because it is connected to 1, 2, and 3 carbons. So that tertiary benzylic has a hydrogen over here, and this hydrogen is going to be the tertiary benzylic hydrogen. So if I go ahead and I lose this hydrogen, and instead now of this hydrogen, I'm going to end up having a radical, then it's going to be a tertiary benzylic radical. Vinylic hydrogens are hydrogens that are connected to the vinylic carbons. And the vinylic carbons are the carbons of the alkene. So this is considered to be a vinylic carbon, and this is considered to be a vinylic carbon. So the hydrogens around these carbons are vinylic hydrogens. So that is a hydrogen here, 2 hydrogens, and a hydrogen over here. So all of those are considered to be vinylic hydrogens. Now, these hydrogens, they are connected to an sp2 hybrid carbon. So each of these carbons is an sp2 hybrid carbon. And we know that sp2 hybrid carbons, they are electronegative. So we do have a strong pull of electrons towards the carbon. So that is going to make each of these sigma bonds in there a strong sigma bond. And the reason why it's a strong, because let's say, for example, if you lose these hydrogens, you are going to generate a vinylic radical. And that radical is completely unstable. So this is going to make that bond between the sp2 hybrid carbon and the hydrogen to be a stronger bond because you generated an unstable radical. So whether you form the radical on this carbon or whether you form the free radical on the adjacent vinylic carbon, the possibility of forming a vinylic free radical to start with is very small because the radical that you're forming is unstable. So we conclude that the allylic and the benzylic radicals, they are stable radicals, and the reason they are stable because the sp3 carbon hydrogen bond can be broken easily due to the less electronegativity of the sp3, and that will generate a stable free radical. So if you get a stable free radical, this means that the bond is weak and it can be broken easily. On the other hand, vinylic radicals, these are unstable radicals, and the reason why they are unstable radicals because the bond between the sp2 hybrid carbon and the hydrogen is a stronger bond, so it's harder to break. So if you break that bond and you generate a less stable radical, this means that this radical does not form, and this means that the bond that it came from is a strong bond. If we want to locate the different types of hydrogens, start first with the most stable hydrogen. I know here I have a combination of primary, secondary, and tertiary hydrogens, but at the same time, I have my allylic hydrogens. And the allylic hydrogens, they are the hydrogens on the allylic carbon. I have here 3 types of allylic carbons. So each of these is going to carry an allylic hydrogen. So here I have an allylic hydrogen. Here I have a different allylic hydrogen. And here I have a different allylic hydrogen. This is going to be a tertiary allylic. This is going to be a secondary allylic. And that is going to be a secondary allylic as well. Okay, so all of these allylic hydrogens, they have the possibility of being taken by a radical. In this chapter, we are going to study the reaction of radicals with the hydrogens and how radicals, they take the most stable hydrogen. So this is why if you're given a structure, you need to identify the most stable hydrogen in that structure, meaning that the weakest bond that can be broken, because we said that if you generate a stable free radical, then this means that the bond that it came from is going to be a weak bond and it can be broken easily. So allylic radicals are here the most stable because you have on the other end, you have a regular secondary carbon. So you are going to end up here having a secondary hydrogen over here. This is a secondary hydrogen as well. So these two are going to be secondary hydrogens. If I want to compare the stability of a secondary hydrogen versus a secondary allylic, then the secondary allylic will have a higher possibility for a radical to come and take it rather than the radical come and take those secondary hydrogens. Same thing in there for a primary hydrogen. So this over here is a regular primary hydrogen. Again, to form a primary radical is way less stable. So the possibility of a radical coming and taking this primary hydrogen is pretty much small compared to the radical taking any of the allylic hydrogens. Now, all of these allylic hydrogens, whether they are secondary or tertiary or even primary, whenever they are next to a radical, the radical has the possibility to come and take each one of them. Although the tertiary allylic hydrogen is going to generate the most stable free radical, which is the tertiary allylic radical, but still the secondary allylic radical also forms, and the primary allylic radical, if there is any, also forms. So the radical over here has the possibility to come and take the three different allylic hydrogens if you have three different allylic hydrogens. The radical will not come and take this vinylic hydrogen because this vinylic hydrogen is going to generate a vinylic radical, and we said that vinylic radicals are completely unstable because the bond between the sp2 hybrid carbon and the hydrogen is a stronger bond. For this example over here, locate your alkene. And the idea again is when the radical want to come and take a hydrogen, it needs to be the hydrogen that generates the stable radical, and the hydrogen that is connected to a weak sigma bond. So the hydrogens that are connected to a weak sigma bonds are simply the allylic hydrogens. Here I have two types of allylic hydrogens. I have a tertiary allylic hydrogen, and that is going to be the tertiary allylic hydrogen. And I have here a primary allylic hydrogen. And both hydrogens, they are going to be abstracted by the radical, whether it's a primary allylic and or a tertiary allylic. After all, if you form an allylic free radical over here, you can have resonance, so that is going to stabilize the radical. The radical will not come and take any of these primary hydrogens. We're going to have the same explanation over here if we have two structures. So let's say if I give you two structures and I ask you which one of these structures, so let's say if I'm comparing this structure over here with this structure over here, and I am locating the sigma bond, and I ask you which one of these sigma bonds is going to be a stronger bond. So the rule says that the stronger the bond, the less stable the radical it forms. So the stronger the bond, the less stable the radical it forms. So all what you need to do, you do a homolytic cleavage in there and see the type of radical that is generated by that particular bond. So over here, I do have a tertiary radical generated for each one. Here I have a secondary radical generated. So the stable radical is the tertiary radical. So this is going to be a more stable radical. So this means that the bond that is going to generate this radical is going to be a weaker bond. So that's going to make this bond a stronger bond. If I give you another example over here and locate the two sigma bonds, and if I ask you which of the sigma bonds is going to be a weaker bond. So which sigma bond is a weaker or stronger? So it's a weaker bond. So by definition, we said that a weaker sigma bond is a bond that generates the most stable free radical. So over here, go ahead and locate the first sigma bond and do homolytic cleavage and generate the radicals. And you can easily see over here that I am forming two primary free radicals. Free radical. Now, a primary free radical is not stable at all, and normally it doesn't form. But here, since we are comparing with the stability or the strength of these two sigma bonds, we have to consider the second sigma bond over here. And we're going to do a homolytic cleavage again for that sigma bond and generate the radicals in there. So we're going to go ahead and generate the radicals, and you're going to form here a primary free radical and a methyl radical. Now, methyl radicals are completely unstable. So this is going to make that bond over here to be a stronger bond, and it is harder to break than this bond over here that will be a weaker bond, and it will be easier to break compared to the sigma